Fantastic. So now let's start. Okay. So overall, if you ask me, the over here the plan is to cover all the aspects related to the uh, Linux kernel, Linux user space internals. And if you see what we have got over here to start with is a system call, and then we will be moving on to the processes, the thread synchronization as per the topics. And now one of the key thing to understand is this particular training which we are conducting, it's going to be project oriented. So I expect you to complete the things related to project, and also there are assignments which needs to be completed as a part of this training. So as always, normally my trainings are the assignments oriented, but now I have added one more flavor where we basically have the project as well. So whatever we'll be learning, we'll be applying it to the project. So this will give you more confidence on how to deal with all these aspects and how do they practically fit into the things. So now this system call is basically more from the conceptual level, and it's better to understand this, but from the process onwards we'll be moving on to the things where we'll be looking into the uh, project oriented things. So step by step we'll be moving with a project which I'm going to introduce in the upcoming session. And at any point of time, if you have any questions or so, you could just let me know. All right. So anytime any glitches or a screen is not visible, you can let me know.
Yes, sir.
So, okay, great, fantastic. So what we are going to see over here, what the system call is, system call versus library function, system call tracing, how do we trace it? And of course, on the basis of that, lots of examples. So first of all, Dipanshu, I would like to understand from you what the system call is and what would be the need of it as per your understanding.
Okay. System call basically is needed to communicate with the kernel space from the user
Yeah,
space.
yeah.
To
Okay, okay.
communicate. So
Yes, your
basically, whenever
understanding is correct. Yeah, right. And so what is the advantage it adds? Like, why do we need the system calls to connect with, why do we
basically
need the,
we
yes, yeah, yeah.
basically we need system call just to basically protection so that user space does not uh,
Okay, okay,
does not get matlab, does not get basically kernel does not get interrupted with user space matlab, kernel की memory protect रहे and all the stuff. That's why we need a
okay, okay,
system
okay.
system
All
call.
right. All right, all right. So your understanding is good with respect to the system calls. So now let's look into the stuff. So if you ask me overall, so your understanding is perfect, Dipanshu. Now let's understand it, this particular thing in a much more detailed way. So now if you ask me, we have got three different spaces. So as you rightly told, we basically have something like a hardware space, then we have the kernel space, and then you have the user space. Now, Dipanshu, please be muted. Yeah. All right. So now, if you ask me, this user space is the one where the user space applications execute. So you can say like with the word processor, the browser, and the PowerPoint, whatever we are doing over here. So that's all executes in the user space. And the processes which are executing in the user space, we also call them as they are executing in the user mode. So accordingly, we have something like a user mode. So similarly, other thing which we have got is the kernel space. Now, what is kernel space? It is where the kernel resides. It is where the drivers execute, kernel threads run, and accordingly, this particular mode we call it as a kernel mode. Now, what happens is this kernel mode is the privileged area, and you have got the full access to the hardware when it comes to the kernel space. So, for example, like whenever you want to write into the hardware registers, whenever you want to control to the hardware, you have got the full access in this kernel space. Now, if you ask me, this user space is a kind of unprivileged area. What do I mean by unprivileged area is you basically don't have the access to the hardware directly. So you can't access the hardware directly from the user space. And over here, basically the access is limited. So now if you ask me, like most of the things, whatever we do, it executes in the user space. So here I have one question. What do you feel when I am a root user? Am I executing in the kernel space or am I executing in the user space?
It's in a user space, na?
It's in the user space. Yes, your understanding is correct. So you are basically executing in the user space at that point of time. So lots of people have the confusion, like when you are into the uh, root privileges, you are executing in the kernel mode. So you need to remember, it's like just the privileged, just a kind of like a mode is changed. Like you have more authority, but still you don't have the authority where you can jump to the kernel space directly. So yes, that's correct. So now, what I told was basically from the user space, you can't access any hardware. That means like camera, mouse, or whatever things, the hard disk you can't access from the user space. But that's a big problem. Like if you ask me, user space is the only one through which I can access the system. And now what I'm saying is I'm not able to access the things from the, I don't have the rights to access this. So that's going to be creating a lots of problem. So that's where this kernel provides some service points, some channels through which you can request the services. Now these channels, this service points is what we call it as a system calls in Linux. So overall, if you ask me, even in the Windows system, you will have something called the system calls. So the system calls are the set of interfaces. Like you have some calls like open, read, write, all those kind of things. And these are the one which will help you access the hardware resources in the kernel. Okay, so you are basically requesting the services from the kernel space in using the system calls. So I hope this is clear, Dipanshu.
Yes, sir.
Okay, perfect. So we'll proceed. Just hold on. It seems there is some issue with my video. Okay, I'll just see what is. Okay. I hope my video is clear. It was basically flickering when I was just looking into it.
It is
Okay.
clear now, sir.
Okay. Okay. Fine. All right. So this is what we basically need the system call with. So system call are the set of interfaces which allow you to interface with a hardware devices, be it like a hard disk, the printer, or anything. Now, what is the difference between the user programs and the kernel programs? So if you ask me, they run in the different spaces, as we have seen. They run with a different privileges. And user space as such is not allowed to access the kernel space. But as I told, they will need some services from the kernel space because kernel is the boss. It is the one which will be able to access the hardware. So OS provides the service points for the user program to request the services from the kernel. And that's where we basically need the system calls. Okay, so all right, we have already discussed about this. Now let's move on. So if you ask me, in Linux, we have around 400 system calls. Okay, so all these system calls, if you want to see the listing, you will find it in user include asm generic unistd.h. So let's look into this particular file. Yeah. So if you see these all system calls, so one of the thing which you will notice is you have got the open system call. You would have got a close, ch own. We have got a close and all those kind of system calls. So overall, if you look into the list, Yes, Dipanshu, go ahead if you have a question.
So these are the macros, right?
Yes,
So
yes.
and they already the code is dynamically linked to the dynamically linked. I mean to
Hmm.
say the where is a code of that system call that if it the
Exactly,
code.
exactly. We'll come to that point. We'll come to that point. That's a good question. So I'll help you out with this.
Also, I wanted to know ki whenever the system call is being called, there
Hmm.
was some instruction is called in Intel. It is 0x80, right? To change
Ah,
the mode
okay,
of the.
okay. Right, right.
So from
Yes,
and I wanted to know where from where does it gets called.
yes. You'll be knowing it. We'll be looking into the complete flow. All right. So these are just the numbers. So as you rightly pointed out, these are basically the numbers, and where these numbers, like how do they translate to the calls? That's what your question is, right? Eventually, we basically want to implement it. So where are these things implemented? So definitely in the next slide, you will be getting the answer to this particular question. Okay, so just hold on. Okay. So what do they do? As we have already seen, they provide the layer between the kernel space and user space, and they serve the below purpose. It provides an abstracted hardware interface for user space. So what do I mean to say is, like, be it any device which you are dealing with, be it a mouse or keyboard or printer or hard disk or any other device, you would need to just use this generic set of things like open, read, write, and all those kind of things. So this basically realizes the concept where we say each and everything in Linux is file. Okay, so and also it enhances the system security in the sense from the user space you don't access the kernel, you don't access the hardware directly, because at the user space we might have a limited knowledge about what the hardware is. So we don't need to be bothered about the nitty gritties of the hardware when we are in the user space. So it provides the abstracted view to us. Okay, so now, so here in this slide, your question will be answered, Dipanshu. Uh, how does the system call executes? And where actually the system call lies? All those things will be cleared from this particular slide. Okay, so now if you ask me what we have got the user mode, we have got the kernel mode. Now, in user mode, typically what you will have your application where you are going to invoke the system call. So when I say system call, it can be something like a open, read, write, that kind of stuff. And you will be, let's say over here, just for the example, we have taken XYZ and we are invoking this open. So now as you understand, whatever functions typically you invoke, normally they are implemented in the library. Okay, so you basically have the C library and these functions are implemented in the library. So of course, this XYZ also will be implemented in the C library. So basically these things, whatever like open, read, write, when they are implemented in the libc, we call them as a wrapper routines. Okay, they are basically wrappers. So similarly for the open, there is a wrapper which is being implemented here. But as you understand, these system calls are the one which are eventually implemented in the kernel mode. Okay, they are the one which are basically implemented in the kernel space. So what we need is basically we want a mechanism by which we can transition from the user mode to the kernel mode. So using the system call, you can do that transition. But now as you understand, see, if I just invoke a normal function, let's say I invoke this XYZ and I went into this library function, this was a normal invocation. Okay. So this is not going to transition me to the kernel space. I'm going to remain in the user space. So I need some special mechanisms by which I can make a transition from the user space to the kernel space. And that's where we basically have some special instructions which can cause the trap. So as you told Dipanshu, like int 0x80, now we use a different instruction over here, but any instruction which can cause a trap in the kernel. So when I say trap, basically it's very similar to the exception. So which can basically create the exception. So only with the help of exception, we will be able to transition to the kernel space. So if you see here, what happens is in ARM, you have something like a SWI instruction. So whenever you execute that SWI instruction, it causes the software interrupt. And through this interrupt mechanism, we make a transition to the kernel space. Okay. Yeah. So go ahead if you have any questions.
So basically, this is the one you are saying. Syscall in XYZ
Hmm.
is the one which is causing the trap, and
Yes.
then
Yes. Yeah. So I have written over here a very generic thing like a syscall. But eventually, see what will happen is it will have some instruction, like a instruction which is architecture dependent. So for Intel, it is INT 0x80. Now it's a next one. For ARM, it is SWI. So it's a special software instruction, a special instruction which is very specific to that architecture.
so what I understand ki what is the implementation of system call in user mode is like is to call the trap function and to
Exactly.
pass the system call number and certain function parameter to some registers
Exactly.
so
Exactly.
that once the trap is called the kernel will look into those registers and will call the appropriately system call, right, and their
Yes.
parameter.
Right. Right, Dipanshu. That's the one. That's the one. That's perfect. Your understanding is correct.
Got it.
Okay. Yeah. So now see what happens is from here we have the system call and we will invoke. So see, this is the system call handler. So it's very similar to like I can say the way the interrupts are implemented in the Linux. What you have is basically you will have a top level handler, and from there on you will be redirected to the particular ISR. So here also you have a system call handler, which is like generic, which gets invoked as and when the trap is called. And now from here on, you are going to invoke a specific function which is supposed to service that. So for instance, let's say this XYZ is open. So corresponding to that, you will have a sys underscore open over here, where the where lies the actual implementation of that system call. And now once you are done with the system call, you will go back to the handler and then you are back to this stuff. So now the key
So
thing, yeah, yeah,
yeah,
go ahead.
one thing. So basically, kernel, the the way kernel identifies the system call is by getting
Number.
the number, the
Yes,
which is being passed from the user mode, right? And
exactly.
so basically, it will for example, for sys underscore xyz, there will
Hmm.
be some number assigned to
Yes,
some call,
yes,
and accordingly kernel will call that function. So basically in the whenever the in primarily whenever the kernel boots up, so those system call must be registered somewhere, right? The numbers will be registered in some
yes,
particular memory. There the memory should be fixed, like in
yeah,
this memory this system call is
yes,
residing,
yes,
right?
yes, yes, you're right. I understood your question. Basically, your question is like from the handler, that number, the handler should have that number to invoke that particular system call. Okay.
Basically the address of that particular
Yes.
RAM or whatever.
Uh, uh, Address of the RAM. Why do we need that address of the RAM?
Because how does the kernel knows ki where the sys XYZ is residing?
Mm-hmm.
So
Oh, okay.
must be
Yeah, yeah, yeah.
so
So,
whenever I pass the 40, though it will calculate the address by using whatever the mechanism.
okay, okay. I understood your point. Basically, what you mean to say is, uh, how will kernel know the address of that function? So you are relating it more with like interrupt handlers, the way the interrupt
Yes,
handlers are there.
yes. That the way, yes.
Yes, yeah. So now, if you ask me over here, so I will just clarify your concept. So actually, not that you need to create a vector table over here. See the reason. So you are relating it more with like a vector table, where in vector table you have the offsets and you go and pick up the things from here. So why is that needed? Because that is triggered from the interrupt, from the hardware interrupt. But now in this case, see what happens is it's just a function. So you basically invoke it with a function. Now of course what happens is this, when you cause a trap, for that you will need the vector table. For the handler you will need the kind of vector table kind of thing, because it's a software interrupt which triggers this. So for this, of course, you need to register this in a kind of like a vector table which correspond to software interrupt. But these functions you need not, because it's just the invocation of the function. You see, sys underscore xyz, sys underscore abc, sys underscore open, sys underscore close.
Acha.
So, so that's why you don't need that stuff where you need to track the addresses, because from the handler onwards, it's just a function, function invocation.
Got it, got it.
Okay, I was able to relate to your question. Why did you ask? Because as soon as we talk of the interrupts, typically we have the vector table, but here you don't need. So vector table, of course, this first handler you need it. From there on, you can decode the things.
And all these are user mode system calls being implemented in the libc, right? So whenever we are executing a new program,
Yes,
libc is getting dynamically linked to the program, and then all this.
yes, yes,
Yeah.
yes. That's the case. Okay. All right. So now the key thing comes is like, how do we pass that number? So see, eventually the system call has to invoke the corresponding function. So how would it know whether I need to invoke the sysopen, sysclose, sysread, syswrite? So how does it identify? So as we have already seen in this particular header file, we have the number. So corresponding to that number, we'll have a function. But now the key thing is how do we pass that number from the user space to the kernel space? So that's where we basically have something called registers. We basically use special registers over here. I can say it can be like any of the registers, like in ARM, you can use R2, R3, or any registers through which we pass the parameters. So one of the hardware registers will be used to pass the system call number, because otherwise this handler is same. How would it know which function to invoke? So it's not through the addresses, but it's through the number which we get in that register, with the help of which we say we can have a case statements over here, and we jump to that particular function. Okay, so
Got it.
all right. So I think whatever questions you had in the earlier things, now it's resolved, right?
Yes, sir.
Okay, fantastic. And now see what you can do is like, if you are interested, you could go to in the kernel space. I will just uh, give you one hint, like in case you are interested in looking into the implementation of this system calls. So what we can do is you can go to, okay, here I don't have the kernel source, otherwise I could have shown you, but I'm just telling, I'll tell you, you will find under FS, I think it should be in drivers, SFS, you will find over here something called, uh, I would say like, you can do the grep over here for sys open in the driver FS, or probably in the FS. Let me be muted for some time. Just hold on. Okay, it's a bit noisier, so I'm muted. Dipanshu, give me a sec. You're hearing the noise, right, Dipanshu? Okay, now it's clear. Now it
Yes,
should be.
yeah, it is clear now.
Okay, okay, fine. Okay, so let's move on. Yeah, so what you can do is in the kernel source code, you can look for sys underscore open. It will be probably in the fs directory. Okay, still, so is it like too much noisier?
No, no, your voice is loud and clear.
Oh, okay, okay, great, great. So then I will not interfere because to me it is I'm able to hear some noise. So it's fantastic. So if it is clear, then all right. So now what you can do is you can go to sys, you can look into the sys open under the fs drivers. I think fs.c or under the drivers fs folder, you will be able to locate that implementation. So you can go ahead and look into that stuff. Okay. Okay. All right. So now let me. Okay. So we'll move on. So how does this system call work? So if you ask me, they are implemented as an ordinary function in the Linux kernel. So that's a very important thing to understand. The system calls are implemented as an ordinary function in the Linux kernel, and they execute like any other things in the kernel space. However, the call to that function is not ordinary. We have already seen if you want to make a transition from the user mode to the kernel mode, what you need is basically a special instruction, some trap over there. So when a user space program makes a system call, arguments are packaged up and handed to the kernel. A special procedure is required, as we saw SWI for the ARM and some int 0x80, some instruction uh, for the x86. So it basically varies from the platform to platform. And as soon as the user space application invokes the system call, we say it is executing in the kernel mode. Okay, so basically it makes a transition to the kernel space. So the privileges are switched. So remember one thing, when you are in executing in the kernel space, though you have got the privileges, but the context is a user space process context. Okay, so you will be remaining in the kernel mode till the system call exits, until the system call completes. So kernel will transfer back the control, and as I told you, we need basically the special mechanism called a trap mechanism in order to achieve that. Hope this is clear.
Yes, sir.
Okay, fantastic. So system call wrappers, as I have been telling you, we have a wrappers. Typically, we have the open, read, write. So those are basically the system call wrappers which are implemented in the GNU libc library. So open, read, write something, and it's very rare that we directly invoke the system call. So let's say I don't pass on the number and directly do that. And in certain scenarios, let's say I'm dealing with some non-standard system calls where I have implemented my own system call in the kernel space. Even that is possible. We want to do that. So you can implement your custom system calls over there, and you can invoke it using syscall and the system call number. So there is one API called syscall. So let's have a look into that. So you see, the syscall is the API using which you will be able to invoke any custom system call. So now you see, using this, even we can invoke the open. Okay, so if we want, we can even invoke this open with the help of it. But since we already have the wrapper, we don't use this. So let's say you implemented your custom system call in the kernel, you can invoke it using that. For which, of course, you don't have the wrappers in the glibc.
So internally, the wrapper is also calling syscall, na, right?
It might or it might not. See,
Yes.
it can happen because I have not looked into the implementation of those wrappers, but it can invoke that stuff. It can invoke that stuff because the syscall again it will be some function in the library itself.
Yes, this call will be something. Yes,
Yeah,
obviously.
so that's why I would say like see uni std and all those things you are including. So uh, it might or might not we need to look into the implementation, but that's a good question. It might invoke syscall directly over there.
Hmm.
Okay, all right. So now coming back. So how does it differs with a library function? See, normally what happens, we tend to confuse this system calls with a library function. So for instance, when I say open, read, write, and all, so of course those are wrappers, but we still call them as a system calls because what happens, the way they are implemented is they will make a transition to the kernel space. Now, when I say library functions, what are these library functions? Like you deal with fopen, you deal with strcat, you deal with strcmp. So like these library functions, what happen, they remain in the user space. Okay, they are executed in the user space as well, but the system calls are implemented in the kernel space and you make a transition. So that's where it basically is different from the library function. So let's look into. So library function is an ordinary function. It resides in the library external to program, but it executes in the user space only. Okay, and moreover, the call to it is also ordinary in the sense like there will be some function which you will be executing. strcmp is like a very function which executes in the user space. So arguments are placed in the processor register and execution is transferred to the start of the function. So it is typically in the shared library like libc. Example, printf, fopen, get opt, and all those kind of stuff. I hope this is clear.
Yes, sir, it is clear.
Okay, perfect. So another thing where you can distinguish the system calls from the library functions, typically if you look into the library functions, they often return the pointers. For example, if you look fopen, what happens? You basically have the file star pointer which you get from the fopen. And what you return over here is null will indicate the failure. So whenever the pointer you get it as a null, that means you will say, okay, this particular call has failed. System calls usually return an integer. So that's one of the thing which you will observe, like open, read, write, and all, they will basically return you the integer. And these library functions will typically return you the pointers. So for example, when I do this res equal to result is equal to open, Harry, read only. So if it is 0 or greater than 0, it is success. Okay. If it is less than 0, typically we use -1, -2, and all those things. So that is basically a failure. So one of the thing which you will notice over here is like a counterintuitive return of the system call. So what I mean to say is like in your library functions, null indicates failure. But now over here in the system calls, 0 indicates success. Okay, and we typically don't use the booleans over here. And so basically, you can't use the boolean over here because you want to provide the additional information like -1, -2, -3, why it has failed, and if it is successful, what like if there is any success with the additional information, you can get it with the help of these numbers.
Got it.
Is it okay? Perfect. So yeah, so now information about the system calls, you'll be getting it from manual pages, of course, and we use man 2, man 3, man 7, depending on which section of the manual for these particular functions are basically.
So what is 2379?
Yeah, so that basically means the manual section. So if you ask me, so let me tell you, for example, see, when I do man exit, so this can basically show you the Over here, it can show you the shell related stuff. Now I can do manual section exit. So typically, see what happens. There are certain functions which are used for the shell, but you need the C related stuff. So they basically go to the different section of the manual. Okay, different section of the, sometimes what you would have seen, we do man 7, like so it's like when you have the multiple implementations, or like it is used as a multiple places. For example, let me do this thing. Okay, it is taking me to the C variant, but now what happens is sometimes it will take you to the I can say the variant which is specific to a shell built-ins. So in that case, you use man 2, man 3, something like that. Oh,
Okay.
got it? Because the same function might have been implemented in the shell. It will take you to the shell. So we have a different sections of man over there. So that's the significance of this man 2, 3. So say system calls, basically we say two library functions. If we want to get, we use 3. Then for miscellaneous, we use man 7 and then man 9. So these are basically the manual sections.
Got
Clear?
it.
All
Hmm.
right. So info pages are also very useful. So for example, if you want to get the detailed information, you can do info on something. For example, info on pthread. Does it gives me anything? Yeah, so info is like a more detailed one. So whenever you want to get the more detailed information, you can use the info. Typically, some of the times what happen, info might point you to the manual page, but if there is any additional information, it will give you more. So I can say whenever you want any detailed information, you will use info. Okay, so now coming to one of the important aspect, like okay, before moving on, let's give one try to one hands-on. Okay, so what we will have is, yeah, so one of the thing what we need to do is you need to clone this repository over here, zip clone.
So this is mentioned in the website also. This.
Yes, yes, yes. So basically, if you go to the assignment section, so let me
Okay.
just show you. If I
Yes.
go to the assignment section over here and under the courses, you will find the assignments. Okay, so in that you will find the stuff. Yeah, so if you go to this assignment, it will show you this information. So you need to clone this.
Yes. Yes. Got it. Got it.
Okay, so right now it's fine if you are not cloning, but later you could just clone this stuff. So git clone github.com. So I hosted all my things on the GitHub, Embitude LSP. So this will give you this LSP folder. So let me just give it a try. Yeah, so it is. I'll just delete it. I already have it, but just to show you. And this is where you will find your assignments and exercises. So here I would like to try one very simple example. So you see, we have something called the library cat, and we have something called the system cat. So as you understand, what does the cat do? It reads out the file and it dumps those dumps those contents on the screen. So now I have shown you two ways of doing this. So when I say library cat, what I'm using a library functions. Like you will see over here, we are using fopen, fread, and all those kind of stuff. And if you see in the system cat, we are using open and read. So this is where it is differing. So this one is using all the calls which are library related, and this is using the system calls.
So internally, f open
Yes.
and f read will be calling this open read, I think.
Yes, you're right. You're right. Your understanding is perfect. Because internally, see, open all f open will also invoke the open. That's
So
true.
then
Yeah.
what is the benefit of
Yes.
creating f open library?
Yes. Yes. So now see the benefit of creating. So that's a very good question. Actually, many of the guys might have that question. Like here, I'm using this open, and why I'm using f open over here. So one of the biggest advantage of using this f open is it's independent of architecture. So what do I mean by this is now so you see the open read write and all it might be they are eventually like architecture specific. Okay, but when you use this library function, your program is portable. When you use the system calls, your program might not be portable. For instance, like if you see fopen, it will be available everywhere. Okay, it will be available everywhere on every operating system. Typically, when you say Windows also, right, there also you will have a fopen. But so it's like portability across the systems and operating systems. You use this kind of stuff because this is C specific. But this is definitely not the C specific. You might have open in Windows or you might not have. So whenever you want your program to be portable across the operating systems, you use this library functions. And whenever you want to use the low level call, see typically what happens when I have this drivers and all, at that point of time, I prefer using open because this is like more direct and it gives me directly to access to the low level. But if I would be writing a program which should be portable across the systems, I will use fopen.
Got
Getting
it.
it? So that's
Yes,
the
yes.
reason. It's good that you asked me. Actually, that's a very good question. Typically, like I otherwise I would be always in the confusions. When should I use the F open? When I should use open? So that's the call. Typically, see when I deal with this low level stuff, and I know I'm going to deal with Linux only, I will use that. But for my other programs, I will write it at the very high level. This stuff.
Yes, sir.
Okay, yeah. So typically, when you develop your application which needs to be portable, use F open rather than open.
Got
Okay,
it, got
so
it.
so this particular program is clear to you, right? What we are doing here. A very simple thing, open it and read it.
Yes, yes.
Perfect. So let's just give it a try. So we'll be doing a make and let's use systemcat. Okay, let's give the file name. I'll give the file name of the same program itself. So it basically dumps the contents of those file. Similarly, if I do library cat, this will also dump this. So if you ask me, the output remains same, but how do we achieve it? That's where it is differing. Clear?
Yes, sir.
Okay, perfect. So let's now, okay, now we are going to come to the very important aspect of how do we trace the system call. So remember, like when you want to debug the things, like when you run into the problem and you don't know what is happening internally, you can use something like a strace. So strace basically is the one with the help of which you can trace the system calls. Okay, so let me show you one stuff. For example, I have the ls command, right? Now, what system calls it is invoking internally, that I can do it, that I can check with the help of strace. So let me show you. So, so I'll use the strace ls. So whatever is listed, each and every line basically corresponds to the system calls over here. So for example, you see exec, then you will have a mmap, you have the access, openet, mmap, and then you will find a read and all that stuff. Yes,
So
go ahead.
can we do stress on the uh, code we have library cat or what and the system cat so that we can see the
Oh yeah,
difference?
yeah. Right. So let's do that. So stress and for example, let's go to library. Okay, library cat. This is what your question is, right? Dipanshu, we can do the stress on this.
Yes.
Yeah,
Just wanted to
perfect.
see what are the system call listening call.
Yeah, exactly. So now, see, this is library cat, and it is doing all this stuff. Okay, wait, just hold on. Let me just separate it out. Yeah. So we are running this. So when you basically try to open any file, it will try to get this access. Okay, and another thing, see, our call has failed actually. You see, this is showing up. Uh, if you notice here, saying no such file or directory. So let us just provide because it expects some file, right, over here.
Yes, arguments.
Yes, so let me, as an argument, we need to provide this. Yeah, now actually it's going. Okay, here we are we need to see what exactly it is. But still we are getting this stuff. We need to see some library it is trying to load. Where is
I
that?
think it's below one. This one is the old one we are checking now.
Ah, right. Okay, let's let me do this stuff. Yeah, thanks for pointing out. So we have
Again,
it located. Yeah, still we have, but this is something else actually, some library ld.s. So it is trying to load and it is showing. So that's not much of relevance to us. It's open. Yeah, so these are basically library, whatever this program might be needing some libraries to access. So it is trying to do that. And we see over here the read and writing to the string. So we basically want to see where is the read of our things called. Yeah, so eventually you see internally it is going as a write only, writing to the screen, reading from the file. And let's closely look into this is where our, yeah. So it's writing this, see, this is stuff it is writing to one is basically your standard output. It will basically go and write it with this to the standard output. And it will read the file. So let's see where it is reading the contents. It should read from the file also. It's going and it's reading the stuff. So we need to decode like what exactly it is doing at that low level thing. So I think it is reading a lot more stuff and then it is dumping, which it is not displaying over here. Okay. Any questions here? So we basically need to decode what.
yes. No question, sir. So, can we print out the trace for this is for system call, library cat. So
Yeah. So
both
you want me to
both
type?
for system cat now, yeah. So
So
both hashes would be the same
yes, yes,
because
yes. So
internally they are
even
calling this.
yes, exactly. So they are just invoking this stuff. So this is a dump actually, what we are seeing. But yeah, this is where it is happening read and write. So eventually you see it is writing into standard output.
And what is
And
three here in read? Read is some.
yeah. So you see three is basically yeah, that's a good question. So that's basically your file descriptor number. So you would have opened the file, right? At that point of
Mm-hmm.
time, we would have got
Int FT, yeah, that one file descriptor.
where we are opening this file.
We are
Uh,
open 80. I think open 80. No, no,
op
open 80 below. You can see na check. Uh, just go down to the below. This open 80.
Open IT. Yeah, that's the one. That's the one. Yes. But we were using system cat, right? Okay, yeah, we are opening library cat. So this you got is the return value is the descriptor. Yes. So this is the file descriptor, and then you are reading the thing. So you see, whatever is equal to that's the return value.
Mm-hmm.
How many bytes, or like what is the descriptor? So you can see the return value from there.
Stress can be only be run. Can we run stress on the live process also, or we have to restart a process every time?
Oh, okay, okay, I understood. Basically, you mean to say like it's
Already running.
already running, and you want to attach. So there is something. So that's a good question. I can say there is something called ptrace. So we can use the ptrace over there, and let me see if we have the ptrace here. No, we don't have actually. Yeah, so if we want to attach it to the live process, basically it's a ptrace which we use. So from the program we can use it, but I'm not sure if we can use it. I'll just mark this question. So that's a very good question. Like if there is a live process and if I want to attach to it, how do I do that? Sometimes for debugging purpose that would be needed. So let me just make a note of it, this thing, and I will get back on this stuff. Okay, so I would say, let me, uh, press on live or already running processes. How do we do it? Okay, I'll just do some research and get back. But that's a good, very interesting question. Okay, yeah, so let's proceed. Yeah, any other queries, Dipanshu?
No, sir.
Okay, all right. And one more thing, see, in Stress, you have got one more feature. For instance, what we want is, I want to trace only specific calls. For example, open. So what I can do is, I can say uh, Stress hyphen e open at. I want to just trace open at in the. So what it will show you is what all open system calls are invoked. So your purpose is like now you have identified like somewhere in the open there might be some issue. So I just want to trace that. So it looks lot less cluttered. So for example, if I want to trace just the read, I can give over here the read function. Okay, so it will give you all this stuff. So you can trace the specific function call. Sorry, the system call.
Got it.
Okay. Okay, great. Even the signals when you are receiving, you will be able to list with histories. Okay, so now let's come to the pros and cons of the system calls and the library functions. So if you ask me, system calls has a pros, right? They provide you the direct address, direct control, and hence you have got the more control over there, direct using the direct access. Library functions, they may have the overhead. So as you rightly pointed out, so eventually see when you have the open and fopen will eventually invoking open, so it has got some overhead. For example, in library function, when you use fopen, it internally creates the context, the data structure. But what do we achieve with this overhead is basically the portability. So always there is a trade-off. See, if you want to achieve the portability, so of course there will be few calls more. Library functions will give you the advantage, like you don't need to deal with the nitty-gritties of the architecture. You don't need to get into the OS specific things of the system calls. So they are like pretty much OS independent, rather, I would say. System calls may expose the underlying system dependency at times. Because somewhere you say like open is not there, for instance, on any OS, then your program won't work, which we don't want. And what happens is sometimes advantage which library functions operate is offer is like single library function might provide you the multiple might wrap over the multiple system calls. So that's the advantage. Like you don't need to invoke the system calls one by one. Multiple system guys calls might be wrapped in a single library function.
So one thing I wanted to the one thing I wanted to know, the system calls which are being shown in ashtrays,
Hmm.
is this the those names are the exact names which
Okay.
those are the exact names which are present in the kernel.
Oh
So
yeah,
the
you mean to say when I say open, is it like open implemented in the kernel with the same name?
yes, open 80. Yes, we got open 80
Yeah,
na, in
yeah,
whenever
yeah,
we
yeah. Open 80.
association.
So in kernel, do I have the? Actually, that's not the case. So as far as I have seen, it is something like sys underscore open in the
Yes,
kernel.
yeah, every yeah. So
Sys underscore close. Yeah. So now see, after all, what you care about is basically the system call number.
mm-hmm.
So it doesn't really matters whether it is implemented is the same name or not, because what it matters is like what number I get here.
So do we also get the system call number in ashtrays? I think didn't.
Oh, okay, okay. No, no, it doesn't specify over there. In stress, it was not showing, right? Let's give it a try. So yeah, let's see. Yeah, here it doesn't shows you the number, because see what will happen is if it shows you the system call number, it will make the things more complicated, because overall purpose is I want to trace this system call. So now displaying a number over here will make your debugging difficult. Are you getting my point?
Got it. Yes, sir.
Because I need to show this in a neater way so that everyone can understand. So now if we start putting a number over here, that would be very difficult. I need to go into that file and need to see that. Clear?
Got it. Yes, sir.
Okay. So now, okay, so this we have already seen. Now I would like to show you some other examples related to system calls. Let me open that screen. Yeah. So we have something called checkaccess.c. Okay, checkaccess.c. So this is going to be the exercise for you, the assignment which you need to try. So we have something called access system call, where you can figure out whether you have the read access, write access, what all different accesses you have on that file. So using this, you need to complete those to do. So if you ask me, these hands-on which I'm providing you are very small hands-on, like very, I can say over here, like you just invoke that particular function and your assignment will be done. So I would highly recommend like you go ahead and complete this assignments, and typically as I told right, when you do the assignment you get the better understanding of the things. So That's why we basically have, if you ask me, only two sessions in a week. One is basically assignment oriented, where we'll discuss about the assignments and the project related stuff. So, and this one will not take more than 5 or 10 minutes. So go ahead and you can just complete this. And for submitting the assignment, see now in the LMS we have that interface. So you see, I have created over here, there should be a assignment. Yeah, this is the one. Basically, what you can do is you can upload TCZ file over here. So once you are done with the assignments, what you can do is you just upload it here and submit.
Yes, sir.
Okay. So
Hmm.
so just take some. So you say like, see, what happens if you don't do the assignment? Typically, we keep on forgetting the things. But once you would have completed the assignments, you can refresh it very easily.
Yes, sir. Yeah, correct.
Okay, so that's one of the assignment. Apart from this, I would like you to try out this stuff, FCNTL. Now, what is this FCNTL? It is the one with the help of which you can do some advanced operations on the file. So what do I mean by that? That means if you do the man on FCNTL file control system call, what it will show you is a mechanism by which you can place the lock on the file. Okay, you can place the
Lock.
lock. Yes, you can lock the file. So what do I mean to say?
No
Basically,
one can.
yes. So for example, when you have opened, the other guy should not be able to open. So I will just quickly show you the demo of this stuff. Let me just see where I have it. So this is what we want. For instance, FCNTL, and let's say I have this file by name fcntl.c. So when I run this, what it says, it is able to lock the file. Now, what I will do is I'll move to other shell. Let me open another terminal. So here in other terminal, what I will do is I'll run the same command. It should not be able to open it. Hmm, how come otherwise it should? Okay, okay, understand. Actually, that function is not implemented. Okay, just hold on. So we should not come out of that. So I will, it's implemented in system call in my case. So you see, this particular process is blocked.
So even cat will not able to open the file.
Ah, yeah, that's a good question. That's a very good question indeed. See, what happens is this FCNTL will work only if you are using that particular API, only if you are using the system call in that process. So what do I mean to say is just think of it like when you have something like a mutex or so. So the process which doesn't uses that mutex will be able to access it, right? So it is
Got it.
only, so it's like
Hmm.
what we call it as an advisory lock. It's not a mandatory lock. So mandatory lock means at the system level that will be controlled, but this is more at the process level. Yeah, good. You brought up
But
that point.
but
Yeah.
this log FCNTL log is managed by the kernel, right? Internally,
Yes.
kernel is holding the log.
Yes.
Internal kernel is so
Yes.
basically kernel is checking up whether the
Yes.
FCNTL how to
Yes.
implement the FCNTL. It's not
Yes.
implemented in the user space, right?
No, it's not implemented definitely because it's a system call.
Mm-hmm.
Okay, so now let me clarify your confusion. Your confusion is basically FCNTL is there in the kernel space, right? So why kernel is not restricting other processes? from
Yes,
doing that.
yes.
Okay, yeah. So basically, see what happens is it will restrict only the processes which are invoking FCNTL, because if the process is not invoking FCNTL, kernel doesn't knows whether it is being controlled or not. But let's give it a try. Uh, Let me try writing it. So let us do something like this. I will use another file. Let me create another file, echo. So once since you have brought this stuff, let's get the clarifications on this stuff. So 1, 2, 3, I will say I have created one file by name A, and let me use, okay, opening A. And now let me do echo. Let's see what happens. I will do the echo on this stuff. Let's say we place, it's able to do, right? So that means,
We are,
sorry. So just
we have
hold
not.
on. Okay, just let us give A. It's able to write,
Hmm.
or else let me put A, B, C. So though it is logged, but you are able to do the write into that. So what does it mean is actually that particular function has to use that stuff, FCNTL. So this is like an advisory log. So now if I use it like this, sorry, we have given a different file here. Then it is blocked.
Yes.
Okay, so that is a key thing which we need to understand. If it is only when you are using FCNTL, you will be able to uh, restrict the access, otherwise not. So that's why we call it as an advisory log rather than a mandatory log. So this can be very useful for your program. See, whenever you are writing your programs where you are dealing with files and you want to protect the access, you can do it easily with the help of this stuff. So that's where it can be very handy.
Yes.
Yeah, so that's a good. So now let's see when I just you see, as soon as I unlocked it, this guy was able to lock it. Getting the concept?
Yes, sir. Basically, this matlab ki once the lock is matlab gained by the first process, the other
Mhm.
one will be waiting. It will be waiting in a busy waiting, or it will some.
No. It will be put to sleep. Busy waiting means we will be wasting lots of CPU cycles.
Yes, yes, yes. So it will be put into sleep. Matlab kernel will put the process into sleep, and once the
Yes,
lock is released, the kernel will just invoke that process from the sleep,
yes,
right?
right, right, right. That's correct.
Okay.
Okay, yeah. Now there are other things which I want you to look into. So this is one of the basic uh, stuff which I have shown you. Now in this system calls, I have created assignments.txt. So these are the things which I want you to try.
First two we have already discussed. Huh? Use access system call to check the read and
Yeah,
write
this
only.
we have already discussed, and place the write log we have discussed. Now we want to place the read log.
Hmm.
Okay, and then I want to just lock a region of the file. Let's say from the offset 100, from the character byte 100 to 200, I want to lock it. That you can achieve if you want that.
Okay. So even we can log the particular offset.
Yes, yes,
Achha,
yes,
that's a good thing.
yeah. So basically, another thing is like you can check whether the lock is available or not. So see with FCNTL, what will happen is you will get blocked when you try to acquire it. So what we want is basically we want to check whether the lock is available or not. If it's available, then only I will take it, otherwise not. So you can use get lock to get the status. And another thing which I want you to try is get time of the day. So my intention is to print the time. Okay, so whatever is the system time currently I want to print. So you can use get time of the day, local time, and strf time. So you can give this a try.
So by using the system call, we have
Yes,
to find a time. Yeah,
yeah,
got it.
yeah. So get time of the day is a system call. Okay, and then you
Okay.
can use local time and strf time in order to get the formatted output.
And local time is also local time is not a system call, but
It's not a
get time of
system
the
call. Only
it's
get
a
time of day is the system call.
ordinary function. Okay.
Yes, you're right. Another one is R limit. So basically, I want to place the limit on the process, how many resources it can use. For instance, like processor time. So let me just show you this stuff. Man, R limit. There's something called get R limit. Get R limit, set R limit. So you can say like, what is the maximum limit I can have for this particular process. So for example, let's say CPU. So CPU, I should not be using more than 1 second, more than 1 second for of CPU. So once that 1 second expires, your process would be killed, will be stopped. So likewise, you can have something like I believe memory and all is also there. So whatever resources you have, you can always cap a limit on how much of that resource the process is allowed to use. So for example, stack, sometimes we run into the stack overflows and all those kind of things. So with this, we can limit the stack which process can use.
So once if uses more than it will get killed. If what if we
Yes.
wanted that process to get to go into the sleep queue? Is this
Uh,
also possible in our limit? No,
Sorry, please
yeah.
come again. Please come again.
So what I wanted to say ki let's is there any possibility we can also put a process to sleep once it overuses a
Oh
limit?
yeah, yeah, yeah. I think this doesn't helps us achieve that. But let me just mark your question. This could be very handy. Limit to. I'll just get back on this stuff. That's a very interesting question. We'll look into that. So rather than getting killed, I want to survive. I want to. I want it to. But the thing is, like, if you have put the limit in the CPU, right? So 1 second is elapsed, so it has to be killed.
Mm-hmm.
So even if you sleep, like sometimes you will come back, right?
Yes.
So that might not be possible from the memory perspective. Probably we'll have to see. So I'll just do some exploration and let you know on this. Okay, and another one, the final one which I want you to try is, yeah, sysinfo. This is very interesting. It will give you the information about the system resources. Sorry, man, sysinfo. So for example, how much is the uptime? How much is the total RAM you have? How much is the free RAM available? So total swap, all those things, information you will get it here. Okay, so there is this is info. Using that, you can get that information. So all these things I have provided as a to-dos here. Have the to-dos, and for sysinfo, there is a to-do like that. So you need to complete. And if you ask me, like these all things might not take more than 10 to 15 minutes. But the thing is, amount of insights it will give you would be a lot better.
Yes, sir.
Okay. So with this, we are done with this system call session, and let me just summarize what we have seen. So we started with why do we need the system call, what the system call is, how does the overall flow goes like, and then we looked into few of the examples. We also saw the difference between the library functions and the system calls. Okay, so this is all we have for today's live session. Now